Welcome back, and this lesson is about the shell method. These are the 9 problems that are proposed to solve using the shell method. And before we go into solving this problem, we are going to review the idea of the shell problem. The idea is as follows. Before starting to explain, please put the speed of the recording maybe in 1.5 or maybe 1.25 or maybe 1, I don't know. But because the video is very long, you make grabs of the ideas at a higher speed. I'm sorry that this video is too long. I'm sorry. Imagine that you have a cylinder. You have a cylinder of radius RV. This is the cylinder of radius RV. The volume of this cylinder will be pi RB squared multiplied by the h. The volume is the area of the base, pi r squared, multiplied by the h. And this is the volume of the external cylinder. The volume of the internal cylinder will be pi ra squared multiplied by h. And the volume that is between the internal cylinder and the external cylinder, the volume that is here, the volume that is inside here, the volume that fills this space. So you imagine here that there is a door. Wow! You imagine the door rotating through the object inside the object. So the door will appear here. So you imagine someone pushing the door and doing a circular motion around the axis of rotation in a way that the guy will appear here. And now he is the guy. And the guy is here. He has his door in his hand and he's pushing the door and he's making a rotation through the inside of the object that is a cylinder, and he's performing a volume. What is the volume that he performs when he does one round? So the volume that he will perform is the external volume minus the internal volume. In this example, we are going to think that RA and RV are very close. They are not small. They can be 4 meters, but if one is 4 meters, the other one is very next to the 4 meters, maybe 4 meters, 10 minus 6 meters adding to the radius RB. So RB is the same that RA, almost the same, but not the same. So what is the volume that this guy performs when he rotates inside the figure, inside the object? The volume that he will perform is the external volume minus the internal volume. Or, in other words, pi RV square h minus pi RA square h. Or pi that multiply RV square minus RA squared by h. But the difference of 2 square, a square minus b square, is a minus b multiplied by a plus b. So I will write this rb squared minus ra squared like ra minus rb multiplied by ra plus rb. But I make a mistake because it's not is rb minus ra. rb minus ra multiplied by RA minus RB. So I'm here, and now I say, okay, because the two radiuses are very similar, RV minus RA will be as a small radius, DDR, the small radius. RA plus RV will be, because they are very similar, RA plus RV is similar to the radius R, it would be 2R. So the formula that I have created is that the small volume, DDV, that exists inside here, when the guy performs one rotation, the small volume that he will cover will be 2 pi r DDR by H. So I will think now in all the problem like this. I will have a door. This is my door. What is the rotation that the guy will perform? The rotation will be through some axis. Maybe this is the axis. I will see the distance from the axis to this element of through this door, through this tiny door. So this distance is the R. This distance, this is the DDR, and this is the H that will be, in most cases, the value of the function f of x. So I will think something like this. Let's go to do something like this. So I will think about the rotation of a function like this, f of x, rotating through the y-axis. So I will think that I can feel the volume generated by this function when I rotate through the y-axis by many doors, and the size of the doors will be like this. So this is the function, this is the function, this is f of x, and the size of the door, it will be like this. This size, this is my first door, this is one of the door, maybe let's go to do it like this. This is one of the door, and this is another door, and all of them, they are rotating through the axis of rotation. So this is the R of each door, of each element of the area. So the volume, the small volume that each one will generate, so this is another door, and the small volume that each door will generate will be 2 pi by the distance that he is at the door. The distance is r, or the distance is x. 2 pi by x multiply by the area of the door. But the area of the door is f of x by ddx. So this is the small volume. The small volume generates when the guy pushed the door. So here is the guy pushing the door. When the guy pushed the door, he generates a volume. When this guy pushed the door, this other guy pushed the door, he generates a volume. Everyone will generate a different volume because the size of the door, the area, is different here than here. So at the end, the total volume will be the sum of all the volumes generated by all the doors that I can feel in my figure. You may say, but listen, when you do the area of the door, you are not taking into account this area, or this one, or this one. Oh, but remember, we are going to make the door so thin ddx or ddr will be so small that the area will be the area that we are not taking into account will tend to zero when we fill the figure with infinity numbers of doors. Okay, so this is the volume, the small volume, and the total volume will be, the integral of 2 pi x f of x ddx, and you see ddx, it was control all the areas of each door. So it will be from x equal, in this case, from x equals 0 to the final door, to x equal maybe, whatever, 5, to x equal 5. So this is the volume generated by the shell method. It's important to visualize the shell method. So as I said, you imagine always a door. The door perform a volume when you rotate this area inside the object, it will generate a small volume, and the next door will generate another volume. And what we are going to do is to sum all the doors or the volumes that generate every door. So the equation will be, as I said, this one. 2 pi x y of x ddx. If you rotate not through if the figure is rotating in a different way, that the radius is different, if this radius is different because maybe you are rotating through an axis of rotation that the radius is bigger, so we put p of x. P of x is the radius. Okay. So we repeat again. What we have said is that every guy will have an infinitesimal small door. Every guy will go around inside the object, inside the figure, inside, and will generate a small volume. This guy, the big guy, will have a big door. So he will generate a big volume. The other guy that is next to this guy, he will generate a small volume. And the equation for each of these small volumes are 2 pi x f of x, that is the height of the door, by ddx. And the total volume is the integral, is the sum of the individual volumes. So let's go to do it like this, maybe. ddv1 is the volumes that occur when this guy is moving around the figure 1 revolution. vdv2 is the volume that generates when the guy that is next here is doing a 1 revolution, plus ddvn is the guy who produced the last revolution, that is a small volume, is smaller than the first one inside the figure. And the sum of all the volumes, is the total volume, but the sum of all the infinitesimal volumes is the integral of this infinitesimal volume, is the volume. And the expression for each infinitesimal volume is 2 pi x f of x ddx. And this is the equation that we will use. If you do the same through the rotation of the figure through the x-axis, you will find an equation that will say 2 pi y 2 pi y y by dy. 2 pi y. You see this f of x depend of x. So it would be 2 pi y y dy. Okay. Now, if you go to your textbook, you will see nice picture like this one. This is the function. You revolve through the y-axis. When you revolve to the y-axis, the volume that will generate is something like this. Is a Mexican hat, we can say. And you fill the Mexican hat with many doors like this one, with different size of the door. Are the sizes of the door. Many people, you imagine many people pushing infinitesimal doors around the circle. So it will generate a volume. And the volume will generate when you imagine infinity number of doors, infinity numbers of area, is the limit when ends tend to infinity of the sum of the volume generated by every door. And the volume generated by every door is 2 pi x. That is the circumference, the length of the circumference, multiplied by the height, f of x, the height of the door, multiplied by delta x, the width of the door, delta x. So it will be the integral from x equal a, in this case, to x equal v. X will vary from a to v. Okay, and this is another picture to imagine how you split the volume into many shells. Of course, this is the function. You see the function. This is the function. Let me put it in green. This is the function. This is the function. You see, when you revolve through the y-axis, this is the revolving function. This is the function. This is the function. So this is the first shell. This is the second shell. This is the third shell, the fourth shell, the fifth shell. And you split it, the sixth shell, the seventh, but you split it in infinity shells, and what you sum is the sum of the volume of each shell. You sum infinity shells. You sum the volume of infinity shell. So this is the expression. When you go from small divisions, let's say n equal 10 to n equal 20 divisions, to n equal 100 divisions, to infinity divisions, you reproduce the total volume of the object. So calculus, this is an application of integral calculus because this is a Riemann sum. This is a Riemann sum, and what you are doing is summing terms of the Riemann sum. Delta x by f of x. These things is the f of x. F of x by delta x, and the sum is the integral. Okay, wow. Let's go now to solve problems. But before, let me tell you one additional detail that you have to consider. Imagine that I have this figure. Imagine that I revolve the figure, the function, I revolve it through the x-axis. When I revolve it through the x-axis, the figure will be something like this. And here is the volume that I have to consider. Okay, where is my door? My door, if I revolve through the x-axis, my door, the size of my door are like this, are parallel to the x-axis. So this is the size of my door. My door will revolve through the x-axis and will generate a volume like I have done before, but through the x-axis. So my point is, when you revolve through the x-axis, the door, the area should be horizontal area. This is the shape of the area. When you revolve through the y-axis, you consider vertical doors. So horizontal doors for revolving through the x-axis in the shell method, and vertical doors when you're revolving through the y-axis. This is the last point, and now we can do the problems. Let's go to solve problem one. Problem one says the region in the first quadrant. The first quadrant is, of course, here, is bounded by the graph of the equation y equal x. Y equal x is this rectilinear line. X equal 2 is this rectilinear, is this vertical line. This is the line x equal 2. And it's revolved through the y-axis. So we revolve the figure, what we revolve? We revolve this region. So when you revolve this region, it will be something like a cone. Oh, but it will be like a cone, but it will be this part. This is the part that I will revolve, this part. So this problem is ideal to use the shell method. What I will do? I will imagine a door here with an area. So I will imagine a guy here that is pushing the door, this door, and is going around. And it will produce a volume. And the small volume that he will produce, of course, that I will consider vertical rectangles, vertical doors, because I'm revolving through the y-axis. And the small volume generated by this guy when this area, this door, revolve one circumference, one revolution, the volume that will perform will be 2 pi x f of x ddx. And now the problem is solved. You just need to plug in numbers. 2 pi, x, f of x is x ddx. You plug in numbers, you do the integral, and this will be the volume that exists here when you revolve through the y-axis, and you revolve between x equals 0 and x equal 2. And if you do the calculation, will be 60 pi divided by 6. Let's go to the next one. The important thing here is the setup. The important thing here is this guy. To see this guy creating the volume inside the figure. This is the important thing. The setup and the visualization of the guy covering the volume inside the object. Okay, let's go to the next problem. The next problem is the region in the first quadrant, this first quadrant, bounded by the graph y equal 1 minus x. Y equal 1 minus x is this graph. It's a rectilinear line with a slope minus 1, and when x equals 0 is 1, and when y equals 0 is x equal 1. So this is the rectilinear line. and it's revolved through the y-axis. If it's revolved through the y-axis and I pretend to use the shell method, I have to consider vertical doors. Use the shell method to find the volume of the resulting solid. Okay, so if I revolve through the y-axis, what I will have is something like this. What I will have is something like this. And the volume here, the volume inside is what I'm measuring, the total volume. But total volume, the small volume produced by one shell is 2 pi, the x of the shell, this volume, the x of the shell by the height of the door multiplied by the width of the door. So it will be, the small volume will be 2 pi x by the height by d dx. Or in other words, will be 2 pi by x, but the height of the door is controlled by the height, by the rectilinear line y equal 1 minus x. So I will plug in 1 minus x in my equation. And this is the small volume. What is the total volume? The integral from where? From x equals 0 to x equals 1 of this expression. If you do this integral, I think you will find pi divided by 3. The important thing is the visualization. Look for this guy always. Look for this guy. Look for this guy pushing the door and creating the volume. Okay, this is the important guy. He creates a volume. And now the guy will go to the next slice, to the next door, and will create another volume. And he will go to the next door, the next area, and he will create a new volume. And the sum of all the volumes will be the total volume of the object. Now, next problem number 4. The region, again in the first quadrant, bounded by the graph. Now, the problem is similar. The graph is y equal x, the other graph is x equal 2, is this line. But now the difference is that this figure is not revolved through the y-axis, it revolves through the x-axis. When I revolve through the x-axis, I have to consider horizontal doors, horizontal areas like this one. The area will perform, let me draw here, the area will perform a shell. This is the shell, this is the shell. Well, let me make a better picture. So this is y equal minus x when I perform it. This is x equal 2. Now, when you revolve, this area will appear here. So the volume generated by this area is here. Okay, is here. So what will be the equation? The equation will be always the same. 2 pi by the radius by the area. 2 pi, the radius is y. Y is the radius. Where is located the door? At y meters up. Why? By the area. Now the area is a vertical door, so the area is d dy, the size, the width, the vertical width of the door multiplied by this length. Oh, this length is 2 everything minus x. This is this length. This length is 2 is from here. And at this y, this is x. So 2 minus x is 2 minus x is the length of this thing. It's important to realize that volumes are positive quantities. Doesn't exist negative volumes. So if the volume is a positive quantity, you need to multiply things that are positive. The area should be positive. This say that d dy have to go up. The area have to be positive, so this say that this length have to be positive. The radius have to be positive, so this x is have to be positive. So the volume generated by, sorry, not this x is the radius, is here, it's the y. The y have to be positive. So the small volume will be 2 pi by the radius y by the size of the door. The size of the door is this length, 2 minus x of y by d dy. 2 minus x of y is 2 minus y, because x of y of x is x. So x of y is y. So 2 minus x of y is 2 minus y d dy. If you perform the integral between y equals 0 and y equals 2, you cover all the small shells. You cover all the shells. You are summing to all the shells. You are summing to all the shells. All the shells. If you perform the integral, it will be 8 pi divided by 3. Let's go to the next one. The next one say like this. It say, the region of the first quadrant bounded by the graph y equal x. Y equal x is the function whose integral is log of x. It will appear the log of x here. It will not appear because, because something happened. Y is y, 1 divided by x is this graph. X equal 1 is this graph. X equal 1 is this line. And x equal 2 is this line. And I want to revolve through the x-axis. So if I want to revolve through the x-axis, I need to consider horizontal doors, horizontal areas like this. So I will revolve and I will generate, every door will generate a volume. And the sum of the volume generated by every door is the total volume. So the equations say that the small volume performed by one stripe, by one sectional area, is 2 pi. The height of the stripe, the y, d dy here, d dy. Okay, so this is the elements of volumes that I'm going to consider when they rotate is the height y, the width d dy, and this length. And what is this length? This length depends where you are, at what y you are, at what height you are. If you are at this height, below 1/2, because when x equal 2, y is 1/2. If you are between 1/2 and 1, the length is different than here. The length here, the length of this horizontal door is everything. So x of y, that is 1 divided by y, x of y minus 1. So I will sum from y equal 1 to y equal 1/2. But because I want positive volumes, I will sum from y equal 1/2 to y equal 1. So I will sum all the shells that I can perform the volume that is on this. They look like a triangle on here. But when I go from the level y equals 0 to y equal 1/2, the length of the door will be different. The y will be different and the length will be different. So I need to do two integrations. The first integration is from y equal 1/2 to y equal 1 of 2 pi y, the function minus 1, that is the length, the function is x of y is 1 divided by x, this is the x of y, the max, the length of the door minus 1 is this length, is x of y minus 1 is this length. But this formula will work between y equal 1/2 and y equal 1. Between y equals 0 and y equal 1/2 is another setup, because from y equals 0 to y equal 1/2, the length is always from 1 to 2. The length is 1. Oh, so let's go to do it for the second part. The second volume will be the volume 2 pi. The small volume will be, let's go to do it. It is the volume of a cylinder, but let's go to do it in integral form. It will be d dv, will be from y equals 0 to y equal 1/2. The size of the door will be 1. This is d dy, and this will be y. So the expression for the small volume will be 2 pi y d dy by 1. That is the area here. And the integral of the sum of all the elements of the volumes will be the total volume. Well, as a result, you have to sum the volumes generated by this shape, by this part, by this region, and the volume generated by this region. The volumes generated by these regions, the volume generated by this region, is this expression. Check if it is pi divided by 4. I think that I made a mistake. And plus the volume generated by this region. That is here. You integrate from y equals 0 to y equal 1/2. Check the result. Check the total volume. I think I made a mistake somewhere, because it cannot be the same amount. Well, you check it. It's not the question here is the setup. So the setup in this problem say, don't use the shell method. It's not a good method to find the volume, because you need to do two integrals, and the shell method is good when you do only one integral. Okay. Now we do problem 6, that says the region in the first quadrant bounded by the graph y of x is like a parabola, is 4x minus x squared, is something like this, when x equals 4, this is 0, so this is the point, and when x equals 0 is here, so it does something like this. But now this problem is different. It revolves about the line x equals 5. If you revolve about the line x equals 5, this is the 6. The figure will be like this, a symmetrical figure, okay, and we'll do like this. And this point will be, what point will be? 7, 8, 9, 10. What will be this point? If I revolve the 0, this is 5. If I revolve, this is the 10. So let me put the figure correctly. So the figure will start at the 6, and will go to the 10. Oh, now you revolve. So you revolve through the axis x equals 5. Oh, wow. So you consider a stripe, a door, like we'll do like this. You imagine the guy walking through here. So where is the guy? The guy is here. Let's go to put the guy. The guy is here, and he will walk through the door, and he will perform one rotation, and he will generate a volume. So I'm summing all the volumes that this guy will generate, and I will construct the volume of the figure resulting by revolving the function through the y-axis by summing individual volumes. So the key thing here is the setup of what is a small volume. A small volume is the volume of the shell that is here. This shell have a radius, and the radius is this one. This is the radius. And the radius is 5 minus the position where the shell is. And the position where the shell is at the position x. So the radius is this one, and is 5 minus x. So it's 2 pi by the radius multiplied by the height by d dx. The height of the door is y of x. And the size of the door, the area of the door, is y of x by d dx. So this is the expression of the small volume when I revolve it through the axis x equals 5. That is a parallel axis to x equals 0 or the y-axis. So the problem is done. I have to sum the contributions to the volumes of every shell. So this shell will produce a bigger volume because it has a bigger radius. Okay, so now we integrate from x equals 0 to x equals 4, and we imagine that the guy here, let's go to put our guy here. Our guy here is the one that is making the calculation. So he will come here to this door, he will perform a rotation, he will find the volume, he will go to the next door, he will do the same thing with the next door, with the next segments, with the next volume, and the problem is almost done. He summed all the small volumes of every door when he rotates, and the total volume will be this integral, the integral of, and you calculate this integral, it's easy, and you will find a number, and the number represents the volume of this function when it's rotating to the axis x equal 5. And that's all. Now we are going to solve problem number 7. Problem number 7 is, it says find the volume of the torus. A torus is a donut. Is an object that is a donut formed by revolving the region bounded by the circle. This is the circle. This is the circle. The circle is centered at x at 0, 0. So this is the circle. It's a, if you revolve the circle around the axis x equal r, so from the center to this line, from the line x equal r, there are r meters. So this distance is r meters. Okay, this is a point x, and what is the point x? Is from the origin to the point x. And we are going to construct our door. Oh, this is the door that we are going to construct. And we are going to consider half of the circle. So forget about the other half. We will multiply by 2 by the symmetry, and we will find the volume generated by this area, but the door, the area of the door, when he revolves through the axis x equal r. So if I made a figure, the radius will be this distance. This distance will be the radius. And what will be the distance? Well, the r is everything. And the x is from here to here. So the radius is r minus x. This is the radius that I have to consider. Okay, I did this problem in class, and the idea is to create an equation that say, this is the area of the circle. And the area of the circle, this area, will perform a rotation through the axis x equal r and will generate half of the donuts. If you do the one rotation around x equal r, you will imagine a donuts here. So this is the donuts. I don't want to touch the picture. Well, let me touch it here. So this is the donuts, and the circle is here. So this is the circle. Let me do a better picture. So this is the donut. This is the circle. The circle will rotate through the axis, and he will rotate through the axis. He will appear in the other side. And the donuts will appear on the rotation. I'm not so good at making figures. Oh, you see the circle? You see the circle moving? So now he will rotate, and he will perform a donuts. This is the donuts. Okay. And the axis of the donut is this axis. But not very good for each other, but acceptable. Okay. So we need to use the shell method to produce an equation. But before doing the shell method, let's go to do it like we did in class. How we did in class? We said, I have the area of the circle. I perform a rotation of the area of radius r. The center of the circle has a radius r through this axis. This is r. Everything is r. Okay, this is r. From here to here is r. Okay, and the area by the length, by the height, the volume of a cylinder is the area of the base by the height. But in this case, there is not exactly a cylinder. So the volume will be the area of the base by the, you move the area through the length, 2 pi r. So the height will be 2 pi capital R. So the volume will be pi r squared by 2 pi r, And if you multiply this, pi by pi will be pi squared, the 2 will appear, and the r will appear, and this will be the equation. But let's go to redo it using the shell method. Well, as I said, the important thing here is the setup of the problem. I put the door here. I put my guy here, and this guy will push the door, the area of the door, and when he push the door, he will perform a rotation through the axis x equal 5, through this axis x equal 5, and when he do one rotation, he will come back to the point, and he will cover a volume. What is the volume that he will cover? The infinitesimal volume that he will cover will be 2 pi by the radius. The radius is r minus x. The radius is everything minus this. Let's say 5 meters minus maybe half meter. Something positive, because in this equation it's important that you realize that volumes are positive quantity. So the radius have to be positive. The value of the function y of x have to go up, have to be positive, and v dx have to be positive, so you are walking from minus r to r. You have to walk to the right to make d dx positive. In this way, you guarantee that the 3 terms will be positive, and the small volume will be a quantity that is positive, and what you have to do is to sum positive quantity to obtain the total volume. So the problem is almost done. The problem, believe it or not, is almost done. So the small volume will be 2 pi r minus x by y of x. What is the height that exists at the point x, at this point x? What is the height? Well, the function. And what is the function? The function is little r squared minus x squared. Is the equation of the graph. So x squared plus y squared equal little r squared. Don't confuse little r with capital R, that is the radius of rotation. Y is square root positive because I want to take the positive height of r squared minus x squared. So this is y of x. Y of x is square root of r squared minus x squared d dx. Multiplying everything and integrate from x equal minus r to x equal r and multiply by 2 because I have done only the volume of half of the donuts, the upper half of the donuts. So I have to multiply by 2 to include the bottom part of the donuts. So this is just something that it will be 2 by 2, 4 pi. The r, I will have two integrals. One when I multiply r by this, and another integral when I multiply minus x by this. So it will be 2 by 2, 4 pi r by square root of this, r squared minus x squared d dx, perfect, from minus r to r. And the other integral that I will have is 2 by 2 pi, 4 pi multiplied by x, 4 pi x, square root of r squared minus x squared d dx. And now you will say, wow, how I will solve these equations, this integral, if I don't know how to solve this kind of integral? Well, this is the trick. This integral is the area of a semicircle. See why? Because y equal r squared minus x squared is this function. This is the function y equal square root of r squared minus x squared. And the integral of this function from minus r to r is the area of the semicircle. So this, even if I don't know how to calculate, will be half of the area of the circle. The area of the circle is pi r squared. Half of them, pi r squared divided by 2. So this will be pi r squared divided by 2 multiplied by 4 pi r. So it will be the 2 will cancel with the 4 and will appear at 2. The pi with the pi will be pi squared. And the r with the r squared will be r by r squared. So this will be the volume, and it's exactly the same volume that we found here, 2 pi r squared by r. 2 pi squared r squared by r is the same volume. Okay. But you will say, oh, wait, and what happened with this integral? This integral from minus r to r is correspond, I don't know yet how to solve this integral, but this integral corresponds to the integral of a function that is an odd function. And as you remember, and we practiced before, an odd function have an area between minus r and r 0. So this area have to be 0, this integral. So we found the volume. Good. Next question. Of course that you can do a practical problem and say, if I have a donut of radius r equal, let's say, 10 centimeters. So the radius of the donut is 10 centimeters. And I perform and I create a donut, big donuts, of radius 1 meter. Or let's put 2 meters. So the big radius is 2 meters. 2 meters. What volume will generate? What will be the volume of the donuts? And the volume of the donuts will be 2 pi squared, 3.14 approximately squared. So I will put equivalent, approximately, because I'm approximating the pi. Pi squared, r squared will be 0.1 meter. 10 centimeters is 0.1 meters square. By r square, it will be 2 square. And this multiplication will be meters cubic. And this is the calculation. How much is this value? I don't know. You can multiply and you can obtain the value and compare. Compare with 1 meter cube, that is 1,000 liters. How many liters will enter in a donut of 10 centimeters of radius when the size of the donut, the radius of the donut is 2 meters? Wow, big donuts. You cannot eat it. You cannot eat it. Now the following problem 8 say, describe the volume represented by the definite integral 2 pi x cubed ddx. If I see only this thing, it may be difficult to visualize what it is, but I will remember that a small volume will be 2 pi by the radius by the function square by dds. The function square by dds is the area of my door. This is my door. Let's go to put my guy here. My guy here, my friend, is this one. Let's go to put it here, this guy. And this is the guy who is going to move the door to make one revolution and to obtain by the shell method the volume. So the radius will be x, the function will be x squared. So this problem will correspond to finding the volume from 0 to 2 of the graph y equal x squared revolving y equal x squared through the y-axis. And this is the volume of this. And of course the bounded are from x equal 0 to x equal 2, and you revolve the graph y equal x squared. Now I can see that it will appear x cubed. Oh, nice problem. Nice problem. Let's go to the next one. Now we go to solve problem 9. Problem 9 say, describe the volume represented by the definite integral 2 pi from 0 y equals 0 to y equal 1 of the function y minus y 3 half d dy. So the y is changing. So the y changing between 0 and 1, between 0 and 1. And there is a function that I don't know yet which function could be, and the function performs a volume. What is the volume of this function? The volume of this function is consider horizontal doors or horizontal areas. What is the area of one element of this area? Is d dy by this length, x of y. So x of y by d dy is this area, is the area of one element of the horizontal door. Multiply by 2 pi by the height by y. This is the volume, the small volume of this door. So the small volume of this door is 2 pi y by d dy, but this is not x of y. X of y is, if this is y, x of y is everything. This is the length of the door, of the area, and the length is everything, which is 1 minus y, minus x of y. So it's 1, the length of this small area is 1 minus x of y. So the small volume, it will be 2 pi y, I will rewrite correctly, 2 pi y, 1 minus x of y by d dy. And this is the small volume. Now I have the equation for the small volume performed by a function that I still don't know what is the function. But if I compare this equation, this one, y minus, with this equation, this is the small volume, I will realize y by 1 is the y, is here. So y by x of y is the y 3 half. So y multiplied by x of y is y 3 half. So who is x of y? Is y 3 half divided by y. So it's y 1 half. Who is y? Y is x squared. Oh, so I found this represents the volume that is under the curve y equal x squared. Oh, and the problem is solved. So that it represents the volume that is the volume using the shell method. Using the shell method that is under the curve y equal x squared. And the problem is solved. Okay, good luck. I'll see you on class.